In this video, my goal is to give an overview of what is multivariable calculus? How is it different from single variable calculus? What are the big ideas? I in particular want to focus on the geometric ideas and give you some of the major pictures that we're going to see along the way in this course. Alright, so let's dive into our overview. The first thing I want to say is, single variable calculus, what did we focus on? We studied functions. Y as a function of x. That was the core object of single variable calculus. And I'll note that what we studied before had a single input, and it had a single output, an input x and an output y, although sometimes we call those different variable names. In multivariable calculus, we're going to have more variables involved, and there's a couple ways to do this. So one way is that you could just have more inputs. There's a single output y still, but that your function depends on an x1, an x2, an x3, perhaps all the way down to an xn. And in particular, when there is two inputs, I can visualize this really nicely. So for example, I can have a graph like this. This is the graph of y equal to x squared plus y squared. It's very similar to the kind of parabola that we would have had in single variable calculus y equal to x squared. But now there's two inputs, x and y, and then an output, which we'll label as z. And the way I think about this is that at every point in the xy plane, there is some height above that point given as z is x squared plus y squared. Now, of course, you could have many more inputs than just the two that we have here, but because I can visualize nicely in 3 dimensions, I can draw a very nice graph when I've got one output and two inputs. But this is not the only way to do it. For example, let's go back to our single variable calculus case. What we had just done was have multiple inputs, but you could also have multiple outputs. So for example, you could have an x that depended on some function of t, a y, which was a different function of t, and a z, which is a third function of t. In this case, what we have is 3 different outputs, x, y, and z, and one single input, t. And indeed, you can imagine functions that have multiple inputs and multiple outputs together, and indeed, we'll talk a little bit about that in this course. Now, this special case can be visualized in a very different way. Notice that my input variable is called t. And I'm going to basically imagine that as I change time, I'll think of t as time, I'm going to have different x, y, and z locations. So here's an example of this. X is cos of t, y is sine of t, and z is equal to t. I've plotted on my x, y, z three-dimensional coordinate system the point 1, 0, 0. And that's because when you plug in t equal to 0, you get x is 1, and y is 0, and z is 0. Now watch what happens when I increase the value of t. It plots out a little bit like this. It creates a helix. As my independent variable t goes around, I map out the equation of this helix. So this is another type of multivariable function that I can visualize in 3 dimensions. I've got my x, y, and z as 3 outputs, and I can plot those in 3 dimensions. And now I'm using time as my independent variable t, and as I change the t, it plots out different points along this helix. As you change these functions, you get all sorts of different ones. So here's a slightly more complicated example of an x, y, and z as a function of t. And as you can see, it creates this really pretty 3-dimensional picture. And it's a lot of fun to play around with these and see what you get. So what can we do with this? Well, many things. Let's go back to the helix that we'd seen previously. One of the biggest stories from Calculus 1 was computing tangents to some curve. Indeed, I can figure out what the tangent vector at a particular point is, and as I change my t variable, I can send it moving around. That is, I can study the equivalent of the derivative of first-order calculus, which gave us the slope of the tangent line. I can try to figure out what does that look like for these kind of curves as well. So this is going to be the first way we're going to generalize the idea of tangents. Another thing I can do with curves is try to figure out how curvy is a curve. What is the curvature of a curve? In this animation, what you see is something called a circle of curvature. As I move around this curve, at different points, it's more curvy and has a, therefore, smaller circle of curvature, and sometimes it's less curvy and has a bigger circle of curvature. So we're going to talk about the math of this as well. In 3 dimensions, it actually has a little bit more of a complicated picture. There's something called a Frenet frame. And this keeps track not just of how much a curve is curving, but how much it's twisting through space. And these 3 vectors that you see moving around here create a way to encode information about how twisty and how curvy a particular curve is. In In single variable calculus, this was just sort of boring because our curve just went along a straight line. But in multivariable calculus, there's a lot of interesting things to pick out here. The next topic I want to contrast in this single variable and multivariable case is the idea of discontinuities and limits. In single variable calculus, we'd study pictures like this, a little step function, where it had a discontinuity at the point x equal to 1. And one of the things that we described in single variable calculus was the notion of a limit. And a limit was a limit from the left and a limit from the right, and when the limit from the left and the limit from the right were equal, then we'd say a limit existed. But in multivariable calculus, as you can see, it gets a lot more complicated. In this particular graph, there's a kind of funny discontinuity at the point x equal to 0 and y equal to 0. You see there's sort of this little spiky thing that's happening here. Indeed, our graphic is only giving an approximation, but this is really meant to be a perfectly vertical spike at this little spot. It's kind of like folding and tearing this surface at that interesting spot. But because it's multivariable calculus, the notion of a limit is no longer just from the left and the right. For example, I could imagine taking the limit along this red line. So in other words, as I move along this red line and approach from the left and the right along that line, as you can see, you get a relatively high value. It's looking like it's approaching some high value in an appropriate notion of the limit. But if I go around some other direction now, a different red line, notice that now this red line is at like halfway up the height of this little spike here. So if you approach along that red line, you're going to get a different value of the limit. And indeed, if you change the value again and you go down this lower red line, you get a different value again. So we're going to have to talk about how to deal with this notion that limits are not just from the left and the right, they're sort of from all different sides, and maybe sometimes you get different values, and it's going to be a whole interesting puzzle that we're going to have to disentangle. After talking about limits in single variable calculus, we normally move on to derivatives. And the derivative in single variable calculus always gave you the slope of the tangent line. So now I've got in both the left and the right side here a multivariable function, a function of x and y. And what I get is not a derivative, but partial derivatives. If, for instance, when I take the partial derivative with respect to x, what I'm doing is effectively imagining that y is fixed. And this gives me this blue curve, which is a single variable curve in the single variable calculus sense. If you imagine that y is fixed, and then I can say the derivative of that curve is like the slope if you're only allowed to walk in the x direction. Or on the other side, if I say, look, I'm only allowed to walk in the y direction, that my x is fixed, this gives you a different curve, and you can take that derivative in the single variable sense and say, well, the slope in that y direction, that's a partial derivative with respect to y. So we're going to build out this idea of partial derivatives that are going to have a very large overlap with the single variable derivatives that we saw back in Calculus 1. And indeed, I'm not just restricted going in the x direction or going into the y direction. I could go around any direction here. In this graphic, I'm imagining that I'm going in any different direction that I wish. The purple arrow tells me the direction I'm going. And then in that particular direction, I can say, how steep is my mountain that I'm climbing if I'm forced to walk along that particular direction? So we're going to build out this idea of directional derivatives. And it really gives this nice picture that if I'm climbing a mountain and I'm heading in some direction, I can ask how steep is the mountain in that particular direction. All these different derivatives, we're going to find a way to combine into something called a tangent plane. If I have my mountain here and I'm some point on it, I could ask not for a tangent line like we would have back in single variable calculus, but a tangent plane. That is some plane that comes down and just sort of kisses this particular surface that is tangent to this surface in some appropriate sense that we'll have to discuss. And indeed, these partial derivatives that we saw earlier are going to be built into the definition of this tangent plane. One of the biggest things that we did in single variable calculus was optimization. It's one of the biggest motivations for calculus. It's why we use calculus in the real world. We want to know what is the minimum amount of energy to do something in some system. How do I maximize my bank account? Minimization and maximization is something that we want to do all the time. In the single variable case, it was relatively simple. There were minimums, there were maximums, and there were some cases that were neither, that perhaps you just sort of went up, flattened out, and carried on. And all three of those have analogs in the multivariable world. There's minimums, maximums, and neithers as well. But there's also something new, something that didn't come up in multivariable calculus. That was the idea of a saddle point. In this surface, If I focus along one direction, say the one I've highlighted in yellow here, where the y value is fixed to be equal to 0, then it looks like a minimum. It's one way it's a minimum. But if I look in a different direction, setting now x equal to 0, that's the blue, then it appears to be a maximum. And so putting these two things together, where in one direction it's a minimum and in another direction it's a maximum, this is something possible in the multivariable case. We call these saddle points. So we're going to have to spend a lot of effort analyzing how do you find minimums, maximums, saddle points, how do you analyze them, and so forth. Analogs, for example, of the first and second derivative test from first year calculus will come back in multivariable calculus as well. And in fact, we can go even further than this. In an example like this, I have some function, this is the function xy plus 1, and I am trying to optimize it subject to a constraint. I'm saying I want to figure out the maximum, but at the maximum along a constraint, this is the constraint x squared plus y squared is 1. It's a circle in the xy plane, but above that circle, x squared plus y squared equal to 1 in the xy plane, you have this blue curve. And then you want to ask the question, what is the maximum height of the function, but restricted to that particular curve? And as you can see, there are these sort of two high points that you can identify and two low points as well. So we're going to have a method, for example, called Lagrange multipliers that will give us ways to do constrained optimization problems. The final chapter that we're going to talk about in terms of multivariable calculus and its comparison to single variable calculus is integration. In single variable calculus, we're often interested in the question of what is the area under a curve? I have some curve here and I want to know what the area underneath it is. And that was a definition of integration. Well, for a function z is a function of x and y, then I have a surface and I can ask not for an area, but for a volume underneath that surface. Okay, so how can I do this? Well, in single variable calculus, the way we did it was we started by approximating by a bunch of little rectangles. We said, well, the actual area under the curve is a little bit like approximately the sum of these rectangles. And we can do the exact same thing in multivariable calculus. We're now talking about rectangular prisms, but nevertheless, we're adding all those prisms up and it's going to be approximately the volume under the surface. Then the approach that we did in single variable calculus is going to be exactly the same in multivariable calculus. We're going to subdivide again and again and get a finer and finer resolution until finally we can say that the actual area, which is some limit as you break it up infinitely many pieces, they're all infinitesimally small, we get some integral. In single variable calculus, it's a single integral. In multivariable calculus, it's a double integral. We use two integral signs. We're going to talk about how to define this, how to compute this, how to deal with this in all sorts of complicated regions. There's a lot of different integration tricks that are relevant in multivariable calculus that just don't necessarily manifest themselves as interesting in single variable calculus. There's even some integrals that we couldn't do in single variable calculus, but that by interpreting them in a multivariable calculus sense, we will have methods to now solve. In single variable calculus, we pretty much just had Cartesian coordinates and polar coordinates as sort of two different ways to describe the objects we were talking about. But in multivariable calculus, there's actually more. One other coordinate system, for example, is spherical coordinates. Normally, I'd take a point like this, and I would describe it in terms of x, y, and z coordinates. But what if instead I said, first let me consider the distance from the origin to that point and call that rho. And then I will define some angle phi between the z-axis and that particular line. And if I take the projection down onto the xy plane, then I get some nice triangle here. Height of this triangle is rho cosine of phi, and the base of it is rho sine of phi. Then I could define an angle between that line in the xy plane and the x-axis. I will call that the angle theta. And then the sides of the resultant triangle I get in the xy plane are going to give me a rho sine phi sine theta and a rho sine phi cos theta. Okay, I did that really quickly, but the point is this. Using a rho, a phi, and a theta, I have something called spherical coordinates, and they give me a different way to describe how to find points in the plane. And then how do I connect this to integration? Well, imagine I had some region like this 3/4 of what looks kind of a little bit like an ice cream cone with sort of a dome top to it. Then you can come up with a way to integrate in 3 different dimensions with a triple integral here and having some sort of weird integrand rho squared sine phi. We have to talk about how to come up with this. But the point is we can use these spherical coordinates to figure out things like the volume of regions that are well described using this other coordinate system as opposed to Cartesian coordinates. There's going to be a bunch of different coordinate systems. We'll have to figure out how to convert between them, how to do this in general, and so forth. Okay, so that's as much as I'm going to do in this video. That's just a brief overview, and of course there was many other things that we haven't talked about, and we have to go into the details about all of these things and explore the nuances and the complexities in each of those topics. I really love multivariable calculus. I think it's a very rich and beautiful field of mathematics. At one level, multivariable calculus is about taking the things that we did in single variable calculus and expanding them to a higher number of dimensions. But it turns out that there's a lot of really rich and interesting mathematics that happens in the higher number of dimensions that was just perhaps simplified or hidden away when we were only doing single variable calculus. And so this course really is a nice extension of single variable calculus into the higher dimensional domain. Calculus is also really nice because it applies so broadly. Indeed, systems in the real world often depend on more than just the single variable we sometimes act like they depend on in single variable calculus. We live in 3 spatial dimensions, for instance, and have a time dimension as well. So dealing with functions of multiple variables is going to be extremely important. So I'm really excited about this course, and I hope that you are as well.